Hello, and welcome to today's webcast. My name is John Lewis. I'm the Editor-in-Chief for Vision Systems Design. Today's event, Improving Automotive Inspection with Light and Color Measurement Systems, will be presented by Matt Scholz, Automotive Business Leader, Radiant Vision Systems. Before we begin, we wanted to cover a few housekeeping items. If you have any questions or issues during the webcast, you can click on the Ask a Question area of the console. We will try to answer these questions during the live Q&A portion at the end of the webcast. Matt's slides will be available for download today. These can be accessed via the Event Resources section under the Ask a Question area in the bottom left-hand corner of the screen. If you have any audio issues, please try refreshing your page. If this doesn't work for you, or if you have any other issues during the webcast, again, please click on the Ask a Question area of the console, and a member of the webcast support team will work with you to correct your issue. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at vision-systems.com. Before we get started today, I'd like to thank our sponsor, Radiant Vision Systems. And now, it gives me great pleasure to introduce Matt. Welcome, Matt.
Thank you, John. Good morning, everyone. I'd like to thank you for attending. I know it's afternoon for some of you on the east and still early morning for those on the west. But as John mentioned, today we're going to be going over basically what some of the benefits are of using a light and color measurement system for automotive applications. We'll talk about using those systems or using our systems for automated testing, but we'll also touch on R&D and QA applications as well. So starting off with the agenda, I'm going to go through who we are at Radiant Vision Systems for those of you who don't know us. Then we'll go into detail on what a light and color measurement system is, specifically imaging photometers and imaging colorimeters. I'll discuss how they differ from standard machine vision systems. We'll go over the applications that Radiant Vision Systems currently services today in the automotive industry, as well as how to select the appropriate imaging photometer or imaging colorimeter based on your system or application requirements, and then we'll conclude. This is going to be a high-level presentation that goes over basically 6 primary applications and our technologies, but I want you all to know that if you have additional questions or would like additional information on our technologies or the applications that we service, I urge you to ask questions at the end of the webinar or to feel free to contact me directly after the webinar as well. So with that said, let's kind of kick things off. So who are we at Radiant Vision Systems? Well, Radiant Vision Systems is primarily a designer, a manufacturer, and a system seller of high-end scientific-grade CCD imaging solutions that are used to look at automated visual defects across a variety of different display applications and lighting scenarios. Our systems are used in all aspects of the product lifecycle, basically from the R&D development to QA, quality control, inline and end-of-line applications. Radiant Vision Systems has been in business for about 25 years now, and over that time we've positioned ourselves as a global leader in display testing applications. And a lot of the success came from high-end expertise in the consumer electronics industry. With that said, over the last several years we've taken that expertise and we've doubled down on some really interesting new vertical markets, and automotive tends to be one of those, where we're taking all of our greatest expertise, our technological advantages, and our intuitive software platforms and positioning them in different applications like automotive. For those of you who don't know, Radiant Vision Systems is located in Redmond, Washington on the West Coast. However, we do have 3 additional offices that we support customers from, those being in Shanghai, Shenzhen, and Seoul. That said, we also do have a large distribution network that we're able to facilitate and meet customer requirements and customer service in different parts of the world as well, like Europe. Konica Minolta acquired Radiant Vision Systems back in 2015, which actually was a massive advantage for us from a company standpoint. They were able to interject us with the resources that we required to really take the next step as a company, and they've given us the capability to look at new and emerging markets, improve our technology, and really up our staffing capabilities. And because of that, we've been able to really project ourselves in the appropriate direction for massive growth. So, light and color measurements, which is really what we're going to be talking about today. So what does it mean to have a light and color measurement system? Well, Radiant, when we first became a company, we had one goal in mind, and that was to be able to create an imaging solution that could easily replicate and quantify brightness and color the same way that humans perceive it, to give us statistical information on the things that we're looking at, rather than just having some sort of perceived observational scenario. And to do that, we created imaging photometers and imaging colorimeters. In this slide, you'll see, sorry, I think there's a delay in the slide. There we go. In this slide, you'll see that there are two cameras. The big guy is our I series, and the smaller one is the Y series. The I series is our imaging colorimeter that uses a 4-filter-based system to create and evaluate tristimulus values and correlate them to the CIE to ensure that we get accurate spatial representation of light and color. The smaller guy is a monochromatic base sensor that only has the capability of measuring luminance. What's great about both of those solutions, though, is we offer high resolution and high dynamic range for a variety of different applications. High resolution and high dynamic range are really important to identify small, subtle defects in a variety of different lighting and contrast environments. And when we think about automotive specifically, and I'll give an example why high dynamic range is important, if you were thinking about an instrument cluster as an example, an instrument cluster has back illuminated characters, but they also have LED indicators within the same panel. High dynamic range allows us to be able to perceive the very dim illuminated components while also measuring the bright components within the same acquisition. This is something that many technologies that we see in the market, be it machine vision or spectroradiometers as an example, have a hard time being able to actually perceive. So it gives a major benefit to our technology. Second is high resolution, which is really important for a variety of different applications, and we'll get into that a little more. Our systems are used, as I mentioned, through all product life cycles, from the beginning of the R&D development to the end-of-line testing. And what's really great is the same system can be used for all of those applications, and we'll talk about that a little more.
Excuse me, Matt?
Yes, John?
Yeah, I was wondering if you could explain a little bit about how imaging colorimeters replicate human vision.
Right. So we use a 4-filter-based system, and that's called a tristimulus-based system that uses 4 optical filters. Those optical filters are photometrically calibrated to align themselves with the tristimulus curves that the human eye sees from a response standpoint. From there, we're able to get accurate color and accurate luminance, which is brightness, out of any application that we're actually measuring. This is a complex scenario, and it's one of the major differences between using an imaging photometer or imaging colorimeter versus using, let's say, a standard machine vision system that is not calibrated and has no capability of giving you absolute tristimulus information.
Oh, interesting.
Does that make sense?
Yeah.
Perfect.
Yeah, thanks.
So as we move on, let's talk about basically quantifying human inspection. So, as we all know, as humans, we have fantastic visual acuity. Our eyes are extremely sensitive, and we have some of the best viewing cones currently available. However, with that great visual acuity, we're also able to detect and classify unpredictable defects. Our eyes are very attuned to picking up small abnormalities, and we see slight variations in color and brightness very easily. However, when we look at inspecting things as humans, especially when we're talking about end-of-line testing, which is really relevant overseas, we have a couple major issues, and one of that is the fact that we're very inconsistent. Every human is slightly different, and everyone's eyes have aged slightly different, which means we tend to see things just a little different from person to person. Our results are not quantifiable, and we easily get fatigued just due to the nature of our eyes wearing down. Now, when we talk about machine vision's been around for a long time, and there's obviously some major advantages to using machine vision solutions. You know, they give you qualitative results and quantitative information. They're very consistent, and they're extremely repeatable. However, when we're talking about measuring light and color, They have some significant limitations, and the major limitations is their visual acuity. Because as I just mentioned to John, machine vision systems are not photometrically calibrated. They don't use optical filters, which means they're not capable to actually perceive light and color from an absolute standpoint. The second drawback is the fact that machine vision cameras primarily need to have pre-programmed defects embedded into their software. They don't have the ability to look for abnormalities outside of the initial programming. And finally, they're incapable of providing any absolute information, which really is what we're looking for in the automotive industry today. OEMs strive to care about absolute information. So, when we look at human visual acuity and we look at the power of automation, we can come to a conclusion that the photometer and imaging colorimeter take both of those, the pros of both aspects, and combine them into one fundamentally powerful solution. So let's talk about the advantages of an imaging colorimeter over machine vision. Okay. Basically, when we look at machine vision, as I mentioned before, they're incapable of providing absolute information. Basically, what they'll give you is 2D pixel information from a contrast or color threshold. That threshold primarily is defined using some sort of scientific grade solution. The information and the capabilities of detection are based on static tolerances that have to be predetermined. They only provide relative information, as I previously mentioned. And one thing that we notice in the industry is they tend to favor speed over resolution in a lot of factors. They also have poor uniformity, and that comes back to the capability, or not having the capability to be photometrically calibrated. However, when we look at imaging photometers and colorimeters, we're providing a solution that has been absolutely calibrated, following NIST traceable calibration criteria, giving you fundamentally the information you want during the development, QA, or end-of-line testing. The primary information that we get out of an imaging photometer colorimeter is luminance and chromaticity. However, many different values are derived from those two fundamental standpoints. Using the optical filters that I previously described, we're able to get a high level of quality from a determination standpoint, and we're able to perceive light and color the way humans do. Our high resolution and high dynamic range put us in a position to be able to adhere to many different varying applications within the automotive industry. And one of the main things that we really excel at using imaging colorimeters and photometers is the ability to detect unpredictable anomalies found in things like displays. So MURA, scratches, dents, etc. In the automotive industry, I mentioned earlier, there are 6 primary applications that Radiant Vision Systems tends to look at. Those 6 applications are as follows: in-vehicle displays, instrument panels, head-up displays, interior lighting, exterior lighting, and material finishes. Each one of those can use the same type of imaging photometer or imaging colorimeter, but we position them in a slightly different way, whether it's using a different software or just looking at different characteristics depending on the application. So in-vehicle displays. Let's start off there. When we talk about in-vehicle displays, we're primarily talking about 5 specific applications within that segmented vertical. We're looking at understanding the luminance and chromaticity from a uniformity standpoint. We want to verify the contrast ratios of the display. We want to detect things like pixel defects to ensure good, high accuracy quality displays are being delivered. We want to look for blemishes and abnormalities, which is a MURA detection algorithm. And something that's becoming more and more relevant in the automotive industry today is understanding how our displays react from different viewing angle scenarios. Since pretty much every display inside the vehicle is looked at off-axis, understanding the viewing angle performance of these displays is becoming more and more critical, not only on the OEM side, but for the Tier 1, Tier 2, and Tier 3 manufacturers.
Hey, Matt. May I interrupt for a second? I have another question.
For sure. Yeah, no problem.
Yes, so I know at the beginning you mentioned that Radiant Vision Systems kind of cut its teeth in the consumer electronics industries, and I'm wondering, are the automotive display tests the same as the tests that would be performed for, say, PCs or smart devices, for example?
Yeah, so a lot of the criteria actually is the same. So what people really care about on the consumer electronic side of things is uniformity, understanding the luminance and the color shifts within the display. So if you have a red display, you want to ensure it's accurately red and not have a pinkish or orange tinge. They also look for things like pixel defects. They're looking for MURA, whether it be edge MURA, so blemishing, flash lighting, things of that nature. And those are all the same criteria that we see in the automotive industry when we talk about displays as well. A quality display has to follow the same fundamental analysis process. So the benefits that we've instilled in consumer electronics are easily carried over into applications within the automotive space.
Very good. Thank you.
No problem. So common tests, like I just mentioned, John, are things like brightness offset and color offset. So we want to ensure that the peak brightness of a display is fairly uniform, that we're not seeing issues within the center or the edges of the display. And the same thing with color offset. We want to verify primarily red, green, blue, white, and black during the analysis process. But there are still other colors that manufacturers want to verify. And we can correlate that information to the CIE chart to ensure we're getting great color accuracy within the display itself. Then non-uniformities are important. So as you can see in the image, it's pretty self-explanatory. If we're looking at a red image or a blue image, we want to ensure that it's primarily blue or red throughout and it doesn't fade off towards the edges to an orange or a pinkish color, really showing poor uniformity. Pixel and line defects are obviously an important test because that shows quality of a display. Consumers don't want to see defective displays implemented inside their vehicle or any other type of application. So being able to quickly characterize those, grade them, and create pass-fail scenarios is something we can do quickly on the fly. Light leakage is probably the biggest problem that automotive displays see today, and that's due to the embedding process and the optical bonding process of the display. As a display gets embedded into a console or center stack, there's pinching that happens on the side of the bezel. This causes what we call light leakage. Some other people refer to it as flash lighting. And we have algorithms to quickly detect, grade, and characterize that type of defect to ensure that it meets the quality standards set by the initial manufacturer. Then MURA testing, we're looking for blemishes and abnormalities found in high contrast areas. Image sticking, we want to ensure that slides are changing with the appropriate inputs. And finally, viewing angle that we characterize. And just to give you a little more information on viewing angle, our capabilities are able to measure plus or minus 60 degrees for luminance and chromaticity across any display. And what's nice is our viewing angle solution is an add-on to our existing system that gives us a strong benefit in the marketplace that really no one else is currently offering. When we talk about display MURA testing, there are a couple things. What we want to do with our software and our imaging system is we want to be able to identify and we want to be able to isolate different types of MURA. What's nice is we can take a single image of a display, let's say black as an example, and we can characterize 3, 4, 5 different types of MURA within that same environment. We can then score that MURA appropriately, and we can create specific pass-fail criteria based on the end user's criteria and severity tolerances. This means that although we might find one specific small defect in a display, it might not be as problematic as one might think, and it might be approved as an appropriate bin. However, if we look at some of the examples here, like if we look at item number 4, you can see that that is a fairly large blemish. That is something that clearly would not be accepted from a quality standpoint, and we can characterize it, we can inform what the just noticeable difference is, relay what the physical size is, whether it be in pixels, millimeters, centimeters, etc., giving the end users the appropriate information they need when characterizing their displays. Display testing is an extremely big part of what Radiant has to do, and although this is really just a quick high-level overview, we really offer a lot of additional detail and capabilities, and I urge everyone listening to reach out to us for additional information if they need it. So moving on to instrument panel harmonization. Instrument panels are a big part of the automotive cockpit. Really, they give us a sense of style, and they give us a perceived view of the OEM's brand. The interior of a Mustang looks very different than a Ford Focus, and that is in large part to design and harmonization. But both of those brands care about one thing, and that's quality. And what's important when we look at the interior is ensuring that the same level of quality and brightness and color is perceived throughout the entire cockpit. So if we look at the applications that we currently service, we're primarily talking about measuring indicators, telltales, control components for uniformity. And those are in things like your prindles, your instrument clusters, they're in your speedometer. And we're looking for, obviously, luminance and chromaticity. And one of the big challenges that this industry faces when you're making backlit components is the fact that there are so many different LEDs being used today in the industry. And I spoke with very many customers that say one of their biggest problems is understanding the dominant wavelength. And that's because they could end up with 6 or 7 different bins from their LED manufacturer, and they need to be able to characterize those and understand that they're getting the right intensity and the right color uniformity coming out of them. So the fact that we can offer this type of testing capability is really important. So when we talk about measuring harmonization of instrument panels, what does that exactly mean? Well, it means we want to be able to capture a sample like the image we see up here. So basically what we're looking at is a speedometer dial. There are 3 separate sections, each with varying illumination components, different colors, indicators, and even displays. What Radian is able to do is we're able to take a very quick snapshot of this entire platform, characterize it for luminance, chromaticity, general uniformity, adhere to different color criteria based on vendors or OEM requirements, and generate pass-fail criteria. And this is all done using an intuitive software platform that Radian has recently come to the table with. This software platform is part of both our TrueTest platform and our photometric platform. And basically we call it the automatic points of interest. The benefit of the auto POI is what I'll call it from here on out, is the way that we give users information. So previously in the marketplace, what you would normally do is you would have your traditional method. So you'd have a static POI. Basically what you would do is you would use a software, you would define a region, you would set a threshold. That threshold would then try to mitigate some of the background information to give you an accurate reading of the light and color coming out of your indicator. However, there are some problems with that old method. One, you're not sure exactly where the refinement is happening, so you have the potential of induced error. Second, you have limitations on the information that is being perceived. If you look at the Radian method, you'll see that we have a green outline around the indicator. What this has done is we've been able to go in, identify the shape, identify the color and the luminance, and we took the 5 different corresponding outlines and we've converged them into a single point of interest. That single point of interest now is giving us the mean or the average of the analysis criteria we care about, specifically luminance and chromaticity and things derived from it. This type of information is exactly what OEMs and Tier 1s and Tier 2s are starting to look for, especially at the end of line, where absolute information is becoming more and more relevant. One of the major benefits of our solution is the fact that regardless of orientation, we can still identify any shape, icon, telltale, regardless of size, color, etc. A traditional method, if we were thinking of an end-of-line tester, would require you to go in, draw your specific regions of interest, as you can see in this slide, and then take your measurement, look at your analysis criteria, and find some sort of reporting. However, in end-of-line testing or even in R&D applications, alignment can sometimes be an issue. And you can see with the traditional method, if we were misaligned slightly, we would actually end up with inaccuracies in our data, and we could end up failing or passing inaccurate panels. Using the radiant method, it has no input on whether the orientation is perpendicular, whether there is any sort of rotation to the panel itself. The benefit here is we fill the field of view using our auto-POI algorithm to rectify the situation and get the analysis criteria we care about. We also have the capability of characterizing different environments or different icons based on color and physical size. On the right-hand side, we have a variety of different colors. You'll see red indicators, yellow indicators, and even a green indicator. What's nice is we can actually measure all of them simultaneously with the radiant method, create different pass-fail criteria based on each corresponding component, and then characterize them based on specific color regions. Where with the traditional method, if you were running 3 separate analyses, one for red, one for yellow, and one for green, you likely would have to take 3 separate images and run 3 separate algorithms. This induces additional acquisition time and lowers your takt time throughput. One of the major benefits of our technology is the ability to identify accurate color. And we do this by looking at information, whether it's in the CIE space, XY, or CIE U', V'. When you work with OEMs in the automotive business, they all have their own specific colors and very tight color thresholds. So if you're a Tier 1 vendor, as an example, and you're working with maybe Ford, they might come to you with ice blue as a color requirement for the specific panel or application that you're working on. That specific ice blue has a coordinate system that adheres to the CIE space. What's nice about our solution is you can actually create that space directly on the CIE chart, whether it happens to be a rectangle, an ellipse, or a polygon, and any point that you acquire or any statistical information that you get out of a point of interest will directly be applied to the CIE chart. What's nice about that is you get direct feedback on whether the points that you're acquiring meet the specification given to you by the OEM or your specific vendor. It is the appropriate way of actually measuring color and rectifying any issues, and Radiant has implemented this software into both our platforms to ensure users get accurate results. So head-up displays. Head-up displays are a really interesting new piece of technology. When I say new, they've obviously been around for 20 years, but they're becoming more relevant in almost every vehicle today. And if you look at some of the SAE standards and the IHS standards, you can see that they're likely to be the next mandatory piece of technology implemented into vehicles, kind of like the reverse camera. The reason for that is they add a significant safety benefit, where they ensure users are not taking their eyes off the road to look at the center stack, a GPS, or looking at their cell phones that are mounted on the top grille. They allow you to keep your eyes on the road, looking ahead of you, but still getting the information you need, whether you're looking at your speed, you're looking at your GPS, or even with some of the augmented reality applications that are being introduced, increased safety awareness.
Excuse me, Matt?
Yes.
Oh, yeah, I'm just curious. Are you going to get into talking about some of the features that the automakers really need to be sure to measure in a head-up display?
Yeah, for sure. So in the next couple slides, I'm going to talk about some of the important aspects of head-up display testing and how our system and our technology mitigates a lot of the issues people have had up until now.
Oh, that's great.
So head-up displays. As always, using an imaging photometer colorimeter, we want to characterize luminance and chromaticity. But more importantly, we also need to understand what's happening with our projected image out within the infinite plane. So we want to characterize things like distance, size, and scale. We want to ensure that the appropriate contrast ratios are being used and the right lighting environment is being displayed, whether we're driving at night or during the day. Since we're looking at a projected image, looking at that during daylight environments means that we need to ensure that we're upping the intensity distribution coming out of that display, and we need to characterize that for uniformity. The same thing can be said for nighttime settings, and our system provides a really intuitive way of doing this. So when we talk about looking at images out on the infinite plane, we're basically talking about identifying projected displays or projected images out around 2 to 5 meters. This is the typical range that we see in heads-up displays today. Using our technology, which is conveyed from the electronically controlled lens that all of our systems use, we're able to identify things like focus distance, rather than having to look at manual adjustments. We can tell you the physical scale, the physical size, and from there, we can then look at things like ghosting of images. We can adhere what the ghosting size is. We can crop down the information, and we can start taking measurements based on evaluation criteria. One of the problems that we see in the heads-up display environments today is the fact that to be able to understand the projected image is quite difficult. It requires a variety of manual measurements using paravans, rulers, off-axis measurements, etc. We eliminate a lot of the manual aspect through using our electronic lens in a fully automated environment.
Excuse me, Matt?
Yep.
Could you tell me what's meant by the term infinite plane?
Right. So in the metrology industry, basically, we consider anything after 1 meter to be in the infinite plane. And everything in augmented reality or in virtual reality or even heads-up displays typically is presented in this infinite plane. The infinite plane is something that can be hard to measure to based on a variety of different conditions. And again, like I said, trying to identify the distance of a projected image in this plane is not an easy task. However, removing a lot of the manual process and a lot of the human user interaction and allowing the technology, the imaging system, and the software to guide you through ensures a more repeatable and accurate scenario. Everything that we see within the virtual reality, augmented reality, and heads-up display environments are always in the infinite plane. It just happens to be, like I said, something outside of that primary 1 meter working distance.
Mm-hmm. Thanks. Thanks for clarifying.
No problem. Now, when we talk about measuring head-up displays or augmented reality, we want to ensure uniformity, but more and more safety standards are being implemented into these environments, and it's important that we make sure, not only as the manufacturer of such equipment, but working with our customers to ensure that they have the capabilities to meet safety requirements, ensure the right environments are being applied, and that their displays meet all safety requirements that exist today for daylight and nighttime settings. For those who want additional information, I encourage you to reach out to us. We're currently involved in a couple SAE committees where we're working to improve the requirements and the testing capabilities for heads-up displays, and we've shared a lot of additional information there that I encourage you all to take a look at. So then we have interior lighting. Interior lighting is all about the feel, the mood, the presence. And there are a variety of different interior lighting components that we look at from a testing platform. Key applications in interior lighting are understanding the distribution of the light sources on the interior cockpit. We want to understand intensity or illuminance distributions, primarily based on distance or angle. Again, we want to understand the light, the brightness, and the color of the perceived light. And we want to ensure that those light sources meet a uniformity and harmonization standard that is similar to the instrument panel clusters. If we have a blue LED light on the door, it should be harmonized to maybe the blue indicators found on some of the instrument panels. Interior lighting, as I mentioned, is more about an experience now and sometimes brand recognition, safety, and even has psychological impacts. There's a general feel to when you get into a car and you start it up and there's a beautiful red glow or blue glow to the environment. And to ensure that that same blue or red is uniform throughout, testing the different interior lighting components becomes very important. The same thing can be said when we talk about things that are not based on just appearance and feel, but have some sort of purpose, like map lighting. It's important that we understand the map lighting distribution of the console. So if you're a passenger and you turn on your overhead map lighting, you have to ensure, as the OEM or as the Tier 1, Tier 2 vendor, that that light source is not blinding the driver. So understanding its cone distribution, its intensity, and its general patterns is extremely important. And this is the type of information that needs to be tested not only in the development phases but also at end of line. The applications that we look at for interior primary things like map lighting, floor lighting, door paneling, graphical lighting. You can imagine when you open up your door and you step out and there's a beautiful Mustang logo on the ground. Those things need to be characterized, not only for safety requirements, but also for quality assurance. However, we don't just look at the finalized assembly aspects. We also look at the initial manufacturing steps. So let's say the lead pipe. A lot of the interior lighting today uses lead pipes for winding and binding processes. We're able to characterize those lead pipes during the manufacturing process or the end-of-line testing to ensure proper uniformity and color distribution is being adhered to, ensuring that that vendor is delivering a quality product from a Tier 2 stage to a Tier 1 and up to the OEM. Exterior lighting. Exterior lighting is really a different beast altogether, and that's because of the nature that people have primarily been testing exterior lighting in. For many years now, exterior lighting was tested using goniometric systems to understand what the distribution pattern is, what the off-axis scenarios might be, and how different test points are adhered to. However, using goniometric systems, it was impossible to measure headlamps, tail lamps, turret signals at end of line. They're just far too slow. Taking hours for a measurement acquisition is not feasible at end of line. However, Radiant's come to the table with a refined software platform. We've listened to SAE committees, we've listened to the ECE standards, and we've taken into account some of the IHS changes that happened last year, and we've come to the table with a software solution and hardware solution that meets development standards and end-of-line testing. So when we talk about key applications, we want to understand and characterize the different light sources. We want to verify intensity distributions as well as illumination distribution patterns and limits. So if we look at this next slide, it basically shows off our PMHL software. So it's photometric headlamp software. I think there's a delay in the slide. Here we go. What we're looking to do here is we're looking to characterize the beam distribution of a headlamp, as an example, against a very uniform wall, some sort of reflective white surface that has a low gain. We want to see things like cutoff points, the general distribution pattern. We want to be able to align things based on maximum gradients, test points that are adhered to SAE and ECE and IHS standards. We want to be able to identify and shift things like the optics in high beams to low beams, which is important not only on the manufacturing floor of automotive vehicles, but at the end-of-line testing of the hardware itself. Another great benefit is the fact that we can extrapolate a lot of that information from a 2D plane. So you'll notice in the second image below, you'll see that there is a distribution. And basically, that distribution is showing us what the headlamp looks like at the baseline, so at 0 meters, so attached to the vehicle, and how that intensity distribution is being perceived out to, let's say, 90 meters as an example. We can also take this information and we can export it to an IES file. We can plot down specific SAE and ECE standard points. You can create your own points based on your specific criteria, whether it's something you've derived yourself or have received from a vendor. And we can generate all these different pass-fail scenarios. And this process can be completely automated for end-of-line. And since last year, the IHS came out and stated that something like 1 in 20 vehicles currently meet highway safety requirements, end-of-line testing for headlamps has really started to emerge, and it's basically a booming requirement right now that very little people can actually facilitate. Radiant feels really confident in our solution, and we're happy to discuss more about it with anyone who has additional questions. And then finally, the last of the 6 applications that we consider in the automotive industry is looking at materials and finishes. So when we look at materials and finishes, we're looking at 2 primary applications. We're looking at surface attributes measurements, so we want to know things like color, finish, reflections, and then we want to identify surface defects, so things like scratches, dings, dents, and general abnormalities that could happen during the painting process. Using an imaging photometer or imaging colorimeter for this application might seem a little strange to those familiar with machine vision, but thanks to our increased capability for high dynamic range and our strong range of application resolutions, we're able to identify things like low and subtle defects and low contrast variations. This is really important for a variety of different applications. When we talk about characterizing surface finishes, our systems are capable using external lighting to identify things like matte paint, glossy paint, translucent or opaque scenarios, and different colors. We want to ensure that the right blue is being painted on the vehicle, or red or green, etc. Now, many of you might be thinking that most of the applications we've talked about so far today involved illumination of some sort. They were all illuminating components. Looking at material finishes and looking at paint, obviously that is a non-illuminated application, but using the right type of external illumination coupled with our high sensitivity and photometrically calibrated solutions, we're able to identify and characterize these different categories and look at things like LAB, which primarily can't be done accurately using other types of technology like machine vision. Detection of surface defects is also something that more and more industries are getting involved in, and whether you're looking at maybe a roof rack on a car, or you're looking at the bumper or the hood, you want to ensure that the finalized vehicle going out is in perfect condition. And thanks to our detection capabilities, we can verify scratches, dents, and other inconsistencies found within the vehicle. This is a really interesting vertical market for us, and it's one that we're constantly expanding within. And again, for those looking for additional information or have questions at the end, please feel free to ask them. So now that I've talked about 6 different applications, you might be wondering, how do I go about choosing the right solution for your application? Now, all of those 6 applications would not use the same resolution. They would not necessarily need a color measurement system, and they probably have different lens configurations. So to start off, the first thing you want to identify when you're thinking of your application is whether you care about verifying color or if you only care about absolute luminance. That will determine whether you use an I series or a Y series. The second thing is understanding the camera resolution. So we offer 4 primary resolutions. We offer a 2 megapixel, an 8 megapixel, a 16, and a 29 megapixel version in our solutions. However, 29 megapixels, although it offers all the bells and whistles, is not necessary for every application. If we were looking at a USB indicator for the interior of a vehicle as part of an instrument panel, and the size of our device under test is only a couple inches, there would be no reason to look at a 29 megapixel. A 2 megapixel would be satisfactory. The second thing we want to look at is the third thing would be the lens. We want to ensure that we fill the field of view with as many pixels over the DUT as possible. So again, if we go back to using, let's say, a USB indicator, well, that is a very small area, so we want to use a narrow field of view lens. There's no point in throwing away resolution on the outskirts of the perceived image. So we can work with you to not only identify the right camera resolution, but also the right lens configuration based on the distance, the size, and the perceived area that you want to measure. The fourth option is software capabilities. All of our systems come with the photometric software database, which is great because it has open access to the API, can be used in applications in R&D, QA, and even production. However, if you want something that is more in tune, more automated, and a streamlined process, you might want to consider our TrueTest environment, which is primarily used for automated applications or high-level production testing of displays. And finally, we talk about integration and fixer configurations. So we can work with you to integrate our solution. We can provide you with the necessary information for mounting, or we can potentially work on fixturing and integration ourselves. We can work with your integrators if you're not the ones involved in end-of-line testing to ensure that communication protocols are met, mounting configurations are met, and that a fully assembled end-of-line solution is available. Radiant is here to basically provide all of the information you need and provide support to customers and even your customers' customers to ensure that the right solution is being implemented and you're happy with the end results that you're getting. So to recap, imaging photometers and imaging colorimeters are used to perceive light and color from an absolute standpoint. They offer a significant advantage over the standard machine vision application thanks to the fact that we can accurately replicate human vision from a color and light standpoint. All of our information is quantifiable, and we create a variety of different inspection limits to perceive and identify the defects or applications you might be working with. By looking at absolute information, you can ensure that you're delivering a high-quality product to your customer at the end of the day. And finally, as I mentioned very early on, one of the strongest benefits of using any of our systems is the fact that they can be positioned for a variety of different applications. If we were using, let's say, an I-16, so our 16 megapixel solution as an example, that fundamentally could be used for 90% of the applications that we talked about today. This gives you a lot of benefit when looking at our type of technology and implementing it across a variety of your different applications. And with that said, I'd like to thank everyone for attending. I appreciate your time, and I hope you found this presentation informative. I encourage you all to, again, reach out to Radiant directly or to me. My contact information is found in this slide, and I'd be happy to talk to you about your applications or our technology in even more detail.
Thanks, Matt. Thank you very much for your insight. We will now begin the Q&A portion of the event. Again, if anyone in the audience would like to ask a question of Matt, please use the Ask a Question area to do so. So with that, let's get right into our first question. Matt, can you describe what kind of light and color values can someone get from the Radiant camera?
Sure. Yeah. So if you're talking about brightness, so luminance, we can easily give you information on candela per meter squared, nits, foot Lamberts, and then things derived from those like illuminance or luminance intensity, which is candela or lux. From a color standpoint, we give you XY, U prime, V prime, dominant wavelength, and we can even give you delta E or purity as an example.
Thanks. The next question asks if external lighting is required in order to perform accurate measurements with your systems?
So external lighting is not required unless we're talking about materials and finishes. So basically one of the last few slides I had when we're talking about looking at defects on paint as an example. That would require exterior lighting. But for all other applications that I talked about today, whether it be interior, exterior, displays, instrument panels, those do not require exterior lighting. In fact, using a darkened environment is often recommended to get the best perceived values and accuracy out of the sample that we're looking at.
Mm-hmm. Great. The next question asks if, can I replace my current vision systems with light measurement systems?
For sure, depending on your application, obviously, but the idea really is to show that we can do primarily 90% of the things that you see with your existing vision system, but then offer you significant advantages when looking at light and color applications. If you truly want to understand what's happening within your DUT or your sample or your product, using an imaging photometer or colorimeter is going to give you significantly more information, data, and capabilities at the end of the day. So replacing your existing vision systems 9 out of 10 times is appropriate.
Okay, the next question has several parts, so I'll just read them, and if you need me to repeat them, I'm happy to do so. First,
Sure.
Can the camera be controlled from MATLAB?
Yes, so the camera can be completely controlled from MATLAB. What's nice, as I mentioned earlier, in photometric or even in TrueTest, we have an open API platform. So if you want to make the appropriate calls to trigger the camera, to have the camera make the appropriate exposure times, pull out the appropriate analysis and reporting, all of that can be done and communicated through MATLAB, LabVIEW, National Instruments, C++, etc. Almost any software language can communicate with our platform.
Okay, that's great. The next part of the question is, do you compensate for lens shading to do a flat field correction / background correction?
So, repeat the question again, just so, because it's kind of a two-part question, so I just want to answer it step by step.
Sure. Yeah, do you compensate for lens shading to do a flat field correction / background correction?
Right. So during the calibration process, we obviously do a flat field correction, and there's two primary benefits to that. One is to ensure that the field of view area that we're looking at is consistent. So one of the biggest problems that people might see using imagers is that if you're looking at a sample perpendicular, so at the center point of the field of view, normally that's where you get your highest accuracy. And as you go out to your widest extent field of view, there normally is a drop-off with competitive solutions. However, with our flat fielding process, we mitigate that and we ensure that we get great accuracy across the entire field of view imaging. In regards to lens shading, the actual lenses that we use help mitigate a lot of that aspect completely. And we actually remove some of the issues that are found due to the lens refraction during the calibration process.
Oh, okay. Great. Yeah. So I'm just sorting through the question here.
Yes.
So there's. I'm wondering what is the time to capture one 8-megapixel color image?
Right. So that is dependent on how bright the sample is. But let's say, as an example, the sample outputted 100 candela per meter squared as a baseline example, and we were using an 8-megapixel imager and we wanted a full color measurement. We'd be able to acquire that in less than 2 seconds.
Okay, and another part of the same question is what is the returned color space? RGB, XY, Y, XYZ, CLAB?
Right. So we use tristimulus filters. So technically we do give XYZ coordinates, but primarily what you're going to see with our system and our software is you're going to get information that relates to the CIE chart. So that means you're going to get either information in 1931 or 1976, so XY or U prime V prime. We don't use an RGB imager, so we don't report back static thresholds or count in RGB data. However, information from, let's say, the color rendering index could also be available.
Okay,
and things
great.
like LAD, which is non-illuminated color, is also available.
All right. What are the limitations on distance and position of the camera relative to the part?
Right. So what's really unique about our situation and our technology is that we calibrate for all possible working distances. And what I mean by that is we calibrate from the minimal focal plane out into the infinite plane. So the minimum focus distance is dependent upon the lens. But let's say we're using a 50 millimeter lens as an example. The minimum focus distance might be 0.4 meters. But we calibrate for 0.4, 0.41, 0.42, 0.53, 0.57, etc., all the way out to 1 meter and after 1 meter. This gives all of our users the utmost flexibility in using our solutions, and we are the only manufacturer of imaging colorimeters and photometers that offer that capability in the marketplace today.
Great. And the last question is, how does the system inspect objects in an HUD, a head-up display?
Yeah. So that question, I'm not sure who asked that question, but additional information on that would be great. However, basically, what we want to look at is we want to be able to characterize things like distance. We want to be able to characterize things like scale. We want to look for different lighting environments. So in a head-up display environment, when you're going through the testing component, you're going to look at probably 4, 5, or 6 different what I call slides, which are different images being projected. One image could be a checkerboard gradient, as an example. At checkerboard gradient, we would look for stark contrast, and we would ensure that the appropriate uniformity is being displayed. If we're looking at a red or a green display, we're obviously going to be verifying color. But then when we look at images or icons being projected, so you can envision speedometer information or arrows or turn signals on the GPS, we're characterizing those as if they were illuminated components, and we're looking for, again, their luminance, their chromaticity, their contrast, their pixel count. So resolution is very important when it comes to head-up displays, so we can actually tell them how many physical pixels or what the physical pixel size is for the illuminated area and components. So we really give head-up display manufacturers and people who are doing testing all of the information that they need in one turnkey package.
That's great, and that answers all of our questions, Matt. Thank you very much.
No problem.
Appreciate it. On behalf of Vision Systems Design and Penwell Corporation, I'd like to thank Matt and all of you for joining us today. This presentation will be archived within 24 hours and can be accessed from the homepage at vision-systems.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. If you have any questions about today's presentation, please feel free to email Matt. His email is on the last slide, or you can also contact me at John, John, M as in Michael, L as in Lewis, at penwell.com. We thank you again for joining us today and look forward to providing you with webcasts in the future.
Thanks a lot.